Our universe has secrets that break the rules. The known laws of physics, they're incomplete. I want to talk about 25 cosmic anomalies, stars that vanish. Voids so large they defy logic. There's a force tugging on spacecraft, millions of miles from home. Our map of the early universe shows a cold spot, a spot that shouldn't be there. The cosmos isn't a settled fact. It's a living puzzle. It's asking to be solved. Pioneer 10 and Pioneer 11. These were two spacecraft sent out farther than anything before. They flew by Jupiter, Saturn, sent back the first close pictures. Then they just kept going out past Pluto into the void. And as they drifted, we kept tracking them, listening for their radio signals. And we noticed something, a tiny discrepancy. They were slowing down just a little bit more than all the equations predicted. The pull was minute, incredibly small. A 10 billionth of Earth's gravity, a tiny acceleration back toward the Sun. But in orbital mechanics, that's a shout. For years, it was a real puzzle. The Pioneer Anomaly, was it new physics, a flaw in our theory of gravity, maybe the pull of dark matter? So the search began, a long process. Scientists looked at everything. The push from uneven heat radiating off the craft, the faint drag of cosmic dust, every possible cause, and the answer, it turned out, was the spacecraft themselves. After decades of data, the analysis pointed to heat from their nuclear power sources, from their electronics, radiating off in certain directions. That radiation carried a tiny momentum, a thermal recoil force. It had been an overlooked detail in the original models, anisotropic radiation, so it wasn't new physics. But it was a profound lesson. Our models have to be exquisitely precise. The secrets are in the details, in the faintest signatures within our own data. That anomaly was a whisper from our own hardware. But then, what about a cosmic event that wasn't a whisper? What about a deafening roar? A signal so powerful it shook the fabric of space and time. Arriving from a source we still don't understand. The universe doesn't only communicate through heat or gravity. It also shoots bullets. These are subatomic bullets, moving almost at light speed, with an energy that's hard to even grasp. They're called ultra-high-energy cosmic rays. Think of a single proton. It's the nucleus of a hydrogen atom, incredibly small. Now imagine that tiny thing having the kinetic energy of a baseball thrown by a professional athlete. That's the kind of scale we're talking about. These particles have millions of times more energy than what we can make in our biggest particle colliders here on Earth. And that creates a huge problem. It's a cosmic speed limit, but not for light for survival, because space isn't empty. It's filled with the cosmic microwave background, the leftover glow from the Big Bang. It's a bath of low-energy photons. For a proton moving at these insane speeds, that background radiation isn't just light. It's like a thick fog. Every time it hits one of those photons, it should lose energy. That was predicted a long time ago. There's a theoretical cutoff, a distance beyond which these particles shouldn't be able to reach us from far-off galaxies. They should just run out of steam, and yet we detect them. Observatories like the huge Pierre Auger array in Argentina see them hit our atmosphere and create massive showers of secondary particles. Their existence is a direct challenge. It means one of two incredible things. Either these particles are coming from somewhere relatively close by in cosmic terms, from some unknown engine with unimaginable power that can accelerate matter like that. Or our understanding of how particles lose energy across those vast distances is just wrong. So what could be the gun? Maybe active galactic nuclei, where supermassive black holes shoot out jets of matter. Or cataclysmic gamma ray bursts from stars collapsing. Or maybe something even weirder, like the decay of theoretical super-heavy dark matter particles. The hunt is on to trace their paths back to find the source, but for now, they're just messengers from the void, carrying energy signatures that our physics can't really explain. And if the universe can fire bullets we don't understand, what else is it hiding? Maybe not an object, but an absence, a vast, chilling nothing that could rewrite all the rules. There's a cosmic desert, a place of staggering scale. We've found it. It's called the Boötes Void. If you traveled there, the experience would be unlike any other. For hundreds of millions of light years in every direction, you'd find almost nothing. A handful of lonely galaxies drift in that immense darkness, like isolated islands in an ocean of pure emptiness. The scale breaks our models. We know the universe has structure, a cosmic web of filaments and clusters with voids in between. But this void isn't a small gap. It's a chasm, a region so profoundly underdense it should be extraordinarily rare, maybe even impossible, according to the standard story of how matter clumped together after the Big Bang. Its discovery in the 1980s was a quiet shock. Astronomers were mapping the large-scale distribution of galaxies, and they found this, a place where the map was mostly blank. The question it asks is simple and deep. Is this a statistical fluke? Did we just happen to look at a uniquely empty part of the cosmos, while the surrounding regions we can't yet see are packed with galaxies? Or does its existence force us to reconsider the very seeds of structure in the infant universe? Some of the more speculative ideas are mind-bending. Could it be evidence of something beyond our universe? A place where our cosmos brushed against another in a vast multiverse, scouring away normal matter in that colossal encounter. That idea remains at the very edge of theory, but the void's very real presence is reshaping cosmology. It's a powerful laboratory for studying dark energy. That mysterious force accelerating the expansion of everything, because in a void with so little gravitational pull from matter, dark energy's repulsive effect is the dominant player. By watching how these empty regions grow, we learn about the engine of cosmic expansion itself. The Boötes Void is a monument to absence. It teaches us that understanding the universe means not just studying the bright and the dense, but also confronting the profound and meaningful nature of nothing. And from this great nothing, our search turns toward the ultimate opposite, an object where matter is crushed into a state so dense it defies all comprehension. That ultimate density is in a neutron star. You take the entire mass of the sun, but squeeze it into a sphere the size of a city, Manhattan. The physics is extreme. The gravity is so immense it crushes atoms. It fuses protons and electrons into a solid sea of neutrons, a state of matter that can't exist on Earth. For decades, physicists calculated a limit, a maximum weight. They thought if a neutron star grew too heavy, the inward crush of gravity would overwhelm the quantum forces holding that dense matter apart. The star would have no choice. It would collapse, vanish into a black hole. That theoretical ceiling was a fundamental rule, but the cosmos tests our rules. There's a star, PSRJ 0740+6620. Through observations of its pulsating X-ray beacon, scientists measured its mass. The result was staggering. This neutron star holds about 2.1 times the mass of our Sun. It's dancing right at the edge of that theoretical limit. Maybe stepping over it. This is a serious anomaly. If the star is truly that massive and remains stable, not collapsing, then something inside must be providing an extra source of pressure. Something is holding up the weight. Our models of the neutron star interior, the equation of state, might be incomplete. What could be in that core? One possibility is the neutrons themselves break down. Under that pressure, they might dissolve into a soup of their constituent particles, quarks and gluons, creating a new form of matter, quark matter, or perhaps exotic particles called hyperons form. They contain strange quarks. They could change the entire pressure balance. These are states of matter predicted by theory but never observed. They would fundamentally alter nuclear physics. Missions like NICER, the Neutron Star Interior Composition Explorer on the space station, are designed to probe this. By measuring the timing and shape of X-ray pulses from these stars, scientists can map their size, infer the conditions within. It's like cosmic tomography, using light to see into the heart of an object where a single teaspoon of material would weigh billions of tons. This isn't just about cataloging strange stars. It's a direct experiment run by the universe on the behavior of matter under the most extreme pressures possible. Every new, massive neutron star we find is a data point. It either confirms our theories or forces a rewrite. They are the ultimate boundary markers, showing us where known physics ends and something new must begin. And if matter can be pushed to such extremes without collapsing, it makes you wonder what other limits are merely suggestions. What if there's a force in the cosmos that doesn't just push boundaries, but works against the very fabric of reality we think we know? A neutron star is something far away. The Flyby Anomaly is closer. It happens right here. When a spacecraft passes by a planet, it uses the planet's gravity. That's a gravity assist. It gives the probe a boost. We've done the math for this for years. The math is precise, but sometimes the spacecraft gets a little more speed than it should, or a little less. The difference is very small, just a few millimeters per second. When you're traveling thousands of miles an hour, it seems like nothing. But in orbital mechanics, where we calculate to the meter, it's a big error. That's the Flyby Anomaly. It was first seen with the Galileo probe on its way to Jupiter. It flew by Earth in 1990 and again in 1992. Tracking its radio signal showed a small shift in velocity. The same thing happened with Rosetta in 2005 and 2007. Each time our models came up short. We account for the planet's gravity, its shape, the pull of the moon and sun. But the probe still got an unmodeled acceleration, a gentle nudge at its closest approach. So what's giving that push or holding it back? For a long time, the main suspect was our atmosphere. Even at high altitudes, there are trace gases. Could atmospheric drag explain it? Most scientists think it's too thin, especially since the anomaly sometimes increases speed, not decreases it. Other ideas go into deeper physics. Could it be frame dragging? That's an effect from Einstein. A massive, rotating body like Earth twists spacetime. It alters the path of things nearby. It's a tiny effect, but maybe it plays a bigger role during these precise flybys. There are other suggestions too. Novel gravitational interactions or thermal effects from the spacecraft itself, like the Pioneer Anomaly. Some studies have explained individual flybys with better models of Earth's atmosphere and rotation, but no single explanation solves every case. The anomaly is still there. It's a reminder. Our most complex gravitational environments, the dance between a planet and a craft, can still hide things. Our calculations are brilliant, but the universe is subtle. If we can be surprised by a few millimeters per second here at home, it makes a bigger puzzle in our own neighborhood seem all the more compelling. The moon has been moving away from Earth for billions of years. It drifts about 1.5 inches farther each year. That's the predictable part, the rhythm we know. But when you measure its motion with a laser, that rhythm isn't perfectly smooth. There's a faint tremor in it. Astronomers have been doing this for 50 years. They fire laser pulses at reflectors left on the moon by the Apollo astronauts and the Soviet landers. They time the light's round trip, a journey of nearly 500,000 miles each way, down to a fraction of a billionth of a second. It's one of the most precise measurements in science, and it shows the moon's retreat has tiny wobbles, small accelerations, fluctuations in its orbital shape, and its mean motion that our tidal models can't fully explain. So something is tugging at it. The main ideas point to processes here on Earth. The dissipation of tidal energy isn't just in the oceans. It happens deep in the planet's mantle, in its semi-fluid core. The way Earth's interior flexes and heats under the Moon's pull is incredibly complex. It's not fully mapped, and these poorly understood processes could translate into subtle nudges on the Moon's path. Other influences come from above. The solar wind, that stream of charged particles from the Sun, and Earth's own dynamic magnetosphere create a tenuous environment around the Moon. The pressure from this space weather might impart a minute force, enough to cause the tiny deviations we see. There are even more profound speculations, though less supported. Could the strength of gravity itself be changing by an infinitesimal amount over time? It's a staggering thought, but the lunar laser data is precise enough to test ideas like that. For now, the anomaly is just a whisper in the data. It shows that even a system as familiar as the Earth and Moon isn't fully solved. Every ping of that laser is a question. It probes not just the distance to another world, but the deepest workings of our own planet, and the constants we believe govern reality. If our Moon's dance holds such subtle mysteries, then what of a force vast enough to choreograph every galaxy in the cosmos? Our neighborhood feels ordinary, but the data says something else. We might be inside a bubble, a huge region of emptiness called the KBC void, named for the astronomers who proposed it. It's not a total nothingness, not like the Boötes void, but it's a significant underdensity, hundreds of millions of light years across. The matter here, galaxies, gas, dark matter, it's all spread a little thinner than the cosmic average. And that subtle fact could be warping our most fundamental view, because from inside this bubble we measure how fast the universe is expanding. We use nearby stars, supernova as mile markers. If we're in a region with less gravitational pull, the local expansion rate could be slightly faster. Space here would stretch a bit more readily. That local measurement gives us one value for the Hubble constant, but then we look at the afterglow of the Big Bang, the cosmic microwave background. It gives us a different, slower value. That's the Hubble tension, two of the most precise measurements in all of science. Disagreeing, the KBC void offers a potential solution. An elegant one. Maybe there's no new physics. Maybe we just have a biased address. Our local bubble makes the universe look like it's expanding faster from our point of view. And that idea directly challenges a cornerstone of cosmology, the cosmological principle. It states that on the largest scales, the universe is homogeneous, isotropic, the same everywhere. If our void is real and significant, it means the universe isn't perfectly smooth. We just happen to live in a slightly emptier part of it. The debate is intense. Is the void substantial enough to explain the full tension? Or is this discrepancy a sign of something deeper, like dark energy changing strength over time? Each new galaxy survey, each map of the large-scale structure, they're all scrutinized for evidence. The answer will reshape our understanding of our place. It forces a humbling question. How much of what we call the laws of the universe is just the view from our particular window? And if our local geometry is this deceptive, what does that say about the true nature of the force driving everything apart? The universe started out hot. In those first few minutes, protons and neutrons came together and made the first atomic nuclei: hydrogen, helium, and a little bit of lithium. That process is called Big Bang nucleosynthesis. The math for it is very clean, and the predictions for how much hydrogen and helium should be there, they match what we see in the oldest parts of space almost perfectly. But for lithium, the numbers are wrong. The oldest stars we can find, the ones made from that early gas, they should have about 3 times more lithium-7 than they actually do. It's not a small difference, it's off by a factor of 3. So there's this mismatch between the theory of the beginning and the evidence, which is written in the light from these stars. For a long time, people have tried to solve this. The first idea was that maybe we don't understand the nuclear reactions well enough. Maybe a reaction rate is incorrect. But even with better colliders and better calculations, the gap is still there. The lithium predicted from the Big Bang doesn't match what we see in these ancient stars. So if the nuclear physics is right, then something else must be changing the record. One possibility is the stars themselves. Maybe these old stars have a way of destroying lithium or hiding it in their interiors. They could be mixing their outer layers, pulling lithium down into hotter regions where it gets fused into something else. But modeling that over billions of years is very hard. And no single idea has solved it for all the stars we look at. That leads to other ideas, more radical ones. What if the physics in those first few minutes wasn't standard? What if there were exotic particles there, decaying and changing the balance of protons and neutrons? Or what if the fundamental constants, like the strength of the nuclear force, were slightly different back then? These are big questions. They challenge cosmology at a basic level. Now the search is going to even cleaner places, distant clouds of gas that have never formed stars. By looking at the light from quasars shining through these clouds, astronomers can measure the lithium abundance directly. They skip the stars altogether. Each new observation is a test, a chance to see if the problem is in the first 3 minutes or in all the time that came after. This isn't just a bookkeeping error, it's a snapshot, a fingerprint from when the universe was an infant. And if that fingerprint is smudged, it means our picture of those first moments is a little blurry. The lithium problem is a quiet voice. It reminds us that our origin story, as grand as it is, might still have pages missing. And if the very first elements hold a mystery, then what about the first light? The cosmic dawn should have left a fingerprint in the darkness. The universe was young then, about 180 million years old. The fireball from the Big Bang had faded to a dim glow. The first stars hadn't lit up yet. Space was just a fog of neutral hydrogen gas, and our models said this gas should have absorbed a certain energy from that background glow. The signature of that absorption would be a faint dip in the radio spectrum at a precise wavelength, 21 centimeters. It's a signal we've hunted for decades. A direct whisper from the universe's infancy. Then in 2018, an experiment called EDGES, a simple radio antenna in Australia, reported something. It saw the dip. But the signal was far too strong, twice as deep as any standard model predicted. That was a shock. The data suggested one of two things. Either the hydrogen gas was much colder than it should have been, or the background radiation bathing it was significantly hotter than we thought. Both possibilities break the standard story. The leading explanation is speculative. What if dark matter was involved? In the early universe, dark matter particles could have interacted with the hydrogen gas, transferring energy away and cooling it down. That would require a new type of interaction between dark matter and normal matter, something beyond gravity. A direct physical link we've never seen. Or maybe there were unknown sources like the first black holes or exotic stars, pumping extra radio waves into the early cosmos, creating a hotter background. The debate is fierce, the stakes are cosmic. This could be our first direct detection of the cosmic dawn, a potential window into the nature of dark matter itself. But extraordinary claims require evidence. The EDGES signal is incredibly faint, buried in a sea of terrestrial radio interference. Could it be an artifact? A subtle error in calibrating out the signal from our own galaxy. Follow-up experiments are searching now, trying to confirm it from different parts of the sky. This deep time anomaly is a ghost in the static. It asks us to rewrite the first chapters of cosmic history. If the universe's opening act holds such a surprise, it forces a question. What if our entire cosmic story is just one volume on a much larger shelf? The infant universe map has a blemish. scientists first saw the full sky image of the cosmic microwave background, that ancient light from 380,000 years after the Big Bang. They expected a tapestry of tiny fluctuations, hot and cold spots, the seeds of all future galaxies. Most of those variations fit the pattern, the statistical fingerprint of cosmic inflation. But one region stood out, a vast cold patch in the constellation Eridanus, so large and so chill it defies easy explanation. We call it the cold spot. It's not just a little cooler. Its temperature deficit and its sheer scale, hundreds of millions of light years across, make it a statistical outlier, a cosmic anomaly written in the first light. According to our standard models, a fluctuation that large and that cold should be extraordinarily rare. Maybe 1 in 100 full sky maps might show something like it by chance. But we only have one universe to observe, so is this our universe's rare fluke or a sign of something deeper? The search for an answer led to two very different paths. The first is an astrophysical one. Could it be a trick of the light? If there's a truly immense void in the foreground between us and the CMB, light passing through it would lose energy. That's the integrated Sachs-Wolf effect. It would make the background appear cooler in that direction. Astronomers have looked. They've found large underdensities, supervoids, in that part of the sky. But here's the catch. The voids we've found, while huge, don't seem quite big enough or empty enough to explain the full depth of the cold spot. The math leaves a gap. That gap opens the door to a far more speculative idea, one that ventures into multiverse territory. Could the cold spot be a cosmic bruise, an imprint from a collision with another bubble universe in the vast inflationary foam of a greater multiverse? In this scenario, the collision would have deposited energy at the boundary, creating a disturbance that imprinted itself as a cold region on our sky. It's a breathtaking thought that we might be looking at direct evidence of a reality beyond our own cosmos. While this idea remains highly speculative, far from the mainstream, its very consideration shows how seriously this anomaly is taken. The cold spot is more than a curiosity. It is a direct test, a stress test for our inflationary models and our understanding of the universe's initial conditions. It asks whether our cosmic story is perfectly smooth, or if it contains chapters of unimaginable violence and connection with realms beyond our own. Every new, deeper survey of galaxy distributions, every more precise map of the microwave background, scrutinizes this cold patch. It is a puzzle written in the negative, in the absence of heat. And if the first light of creation can hold such a profound mystery, it makes the behavior of the most brilliant objects in the modern universe seem all the more strange. Some galaxies aren't just beautiful, they're geometrically perfect. Hoag's object is like that. It's out there, a cosmic bullseye. You have this dense, round core of ancient yellow stars at the center. And then, completely separate, a brilliant ring of young, hot blue stars. There's a clean, dark gap of emptiness between them. It's not a spiral, it's not an ellipse. It's a ring galaxy of such symmetry it looks almost artificial, and its existence asks a difficult question. How does a galaxy become this? Our usual stories don't fit. Most ring galaxies, like the cartwheel, are born from violence. One galaxy punches through the center of another, like a stone thrown through water. The gravitational shockwave sends gas and stars rippling outward in a ring. But Hoag's object shows no sign of a recent collision, no distorted core, no trailing debris. Its core is serene. The ring is perfectly circular and centered. It's as if the violence happened and then everything settled into this impossible calm. So maybe the cause was different, a rare, precise event. A smaller dwarf galaxy could have passed directly through the center billions of years ago. A perfect bullseye hit. The symmetry of that impact and the time since might have let the ring settle into this pristine form, but the odds of such a perfect collision are astronomically low. Another idea steps away from collisions entirely. Maybe the ring is the result of a resonance, a past, gentle gravitational interaction with another galaxy set up a standing wave in Hoag's gas. Like a ripple frozen in time, this wave then triggered star formation only in that precise ring, leaving the core untouched. For now, Hoag's object is a singular masterpiece. A reminder that the universe can craft forms of stunning order from chaos. Through processes we are still learning to see, it challenges our models of galactic evolution. Sometimes the most elegant structures are also the most mysterious, and if a galaxy can be shaped into such a perfect circle, it makes the chaotic, tumbling dance of objects in our own backyard seem even more peculiar. The paradox is in the rocks. Our sun, over 4 billion years ago, was a faint young star. It only had about 70% of the brightness it has now. That's a fact from stellar models. A star like ours gets brighter as it ages, so with that weaker sunlight, the early Earth should have been frozen, a global ice house. A snowball planet, but the geological record says something else. Ancient zircon crystals, some of the oldest minerals we have, show they formed in liquid water. There's even evidence for very simple life appearing not long after. So the question is, how did Earth stay warm? How did it have oceans and maybe life under such a dim sun? That's the faint young sun paradox. It makes us rethink the planet's entire early history. The main solution looks to the sky, a much thicker, primitive atmosphere. One rich in powerful greenhouse gases like methane and carbon dioxide that could have wrapped the planet in a thermal blanket, trapping the sun's meager heat. But getting that balance right is a delicate puzzle. Too much greenhouse gas and you get a runaway hothouse like Venus. Too little and the ice takes over. So scientists run climate models, trying to find the precise cocktail of gases that keeps the thermostat just right. Other factors probably played a role too. Maybe the young Earth was darker, less reflective ice and land, so it absorbed more of that faint sunlight. Its rotation or orbit might have been different, changing how heat was distributed. There are even suggestions the early sun itself might have been more active. Stronger solar winds, more frequent flares, interacting with the atmosphere in warming ways. Each possibility is a piece of a 4-billion-year-old climate puzzle. This anomaly is more than academic. It sits at the intersection of astrophysics, geology, and biology. It defines the narrow pathway a planet has to walk to become a living world. If we can't fully explain how our own home stayed habitable, how can we assess the potential for life on all those exoplanets we're finding? The faint young sun paradox is a humbling reminder. Habitability is a fragile, complex dance. It needs the right star, the right planet, the right history, all aligning in a way we're still trying to understand. And if our own well-behaved sun holds such a deep mystery from its youth, it makes the outright rebellious behavior of other stars seem even more astonishing. A star can keep its secrets right in front of us. Kepler watched hundreds of thousands of stars, and one of them acted stranger than any other. KIC 8462852. Tabby's star, to us it looks normal, a middle-aged yellow-white star, but the light from it tells a different story. It doesn't dip a little the way a planet would. It falls, it plummets, the brightness has dropped by 22%. That's not a planet, that's something blocking almost a quarter of the star itself. Something huge and irregular, the pattern is chaotic. These deep, uneven dips that go on for days or weeks with no set rhythm, that's not an orderly solar system. So the search for an explanation started with the obvious things. Maybe a swarm of comets, thousands of them, on wild orbits, or the debris from a planet collision, a huge cloud of dust and rock. Each idea made some sense, but each had a problem. A comet swarm big enough to do this would be something we've never seen, and the star's heat should have vaporized that icy material. Collision debris would eventually fall into the star or drift away. But these dimming events have kept happening for years. That's when the mystery really caught people. When the natural explanations started to strain, a more speculative one came up. Could it be astroengineering, a Dyson swarm, a collection of energy collectors built by a civilization drifting in front of their star? That idea was thrilling. It turned Tabby's star into a phenomenon. People looked at the data, professional astronomers and citizen scientists crowdfunding telescope time all over the world. The answer was in the light. When something passes in front of a star, it doesn't block every color the same. A solid object, a planet or a structure, blocks all light evenly. But dust scatters blue light more than red, and the observations showed that the dimming was much stronger in blue light than in red. That wavelength-dependent dimming pointed to dust. Fine particles smaller than smoke, so the alien megastructure idea faded. But the mystery got deeper. Where is all this dust coming from, and what's shaping it into these huge, irregular clouds that drift into our view? The main theory now is about exocomets disintegrating as they swing too close to the star, or maybe the breakup of a moon or a dwarf planet, creating a changing debris field. Tabby's star is a lesson, how one strange point of light can pull our curiosity and collaboration, pushing how we observe things. It makes us see the chaotic, violent processes that might shape planetary systems over time. And from the strange story of one star, you look out to a much bigger disappearance, the vanishing of entire galaxies. The spiral of a galaxy looks orderly. It looks like it should follow the rules. The stars out at the edge, they're far from all the mass in the center, so they should move slower. That's how it works in our solar system. The inner planets are fast, the outer ones are slow, but in the 70s, astronomers started measuring. Vera Rubin was one of them. They found the outer stars weren't slowing down. Their speed stayed high all the way out to the edge. The rotation curve was flat. That meant the gravity out there was stronger than it should be, stronger than all the visible stuff the stars, the gas, could provide. Something else was there, something invisible pulling on them, a halo of dark matter, and it wasn't a small amount. It meant most of the matter in a galaxy, over 80%, doesn't shine. Doesn't interact with light at all. We only know it's there because of gravity. That dark matter halo, it's like a scaffold. It holds the galaxy together. Without that gravitational well, the ordinary matter, the stuff we see, it wouldn't have clumped. The flat rotation curve is the direct evidence. It's very clean. But a claim that big, it makes you ask questions. Maybe the laws of gravity are wrong on that scale. There's a theory called MUND, modified Newtonian dynamics. It says gravity works differently at very low accelerations, like out in the galactic fringe, and it can create that flat curve without any dark matter. It's an elegant idea, but it has problems. It can explain the rotation, but then there's other evidence. The way galaxy clusters bend light, a gravitational lensing that shows huge amounts of mass. MUND often has trouble with that, and the cosmic microwave background, the early universe's blueprint, it fits perfectly with dark matter models. For a lot of scientists, all that evidence together makes dark matter the stronger case. Even if it's mysterious, so if it's real, what is it? That's been the search for decades. The main candidate is a particle, a WIMP, a weakly interacting massive particle. Left over from the Big Bang, they'd be everywhere, passing through us, almost never hitting anything. There are detectors deep underground waiting for that one collision. Other ideas are out there, actions or primordial black holes. Each one tells a different story about the universe. This dark matter, it does more than hold galaxies. It sets up the biggest collisions. When galaxy clusters smash together, the normal matter, the hot gas, it collides and glows, but the dark matter, it doesn't interact. It just passes through, and we can see that. Observations show the mass seen through lensing separating from the visible gas. It's a ghostly outline. Proof that it's a real thing, a physical part of reality. Its nature is still a puzzle. A fundamental part of the cosmos we know is there but can't see. And if the universe is full of this invisible mass, it makes you wonder what else is out there, bending reality on the largest scales. We can count the normal matter we see in stars, in galaxies. We can also look back to the beginning, to the cosmic microwave background, and see how much ordinary matter the Big Bang made. The two numbers should match, but they don't. We only find about half of the ordinary matter today. That's the missing Baryon problem. It's not dark matter. It's the regular stuff, just unaccounted for. The idea is it's hiding in plain sight, spread very thin, in the vast spaces between galaxy clusters where the cosmic web has its filaments. There's a diffuse, superheated plasma. The warm, hot intergalactic medium, the WIM. This gas is millions of degrees hot, so it doesn't glow in visible light, and it's so tenuous, just a few atoms per cubic meter, that it's nearly transparent. Finding it is difficult. It relies on tricks. When light from a distant quasar travels to us, it passes through these filaments. Atoms in the WIM, like highly ionized oxygen, absorb specific wavelengths. That leaves extremely faint absorption lines in the quasar's spectrum. It's like finding a chemical signature on a distant beam of light. In X-ray light, we can sometimes see the faint glow of this ultra-hot gas. Where it pools in the densest knots of the cosmic web, where filaments intersect, each observation is a painstaking effort, a pixel added to a map of the invisible. The mystery is also how it got so hot. The suspect is cosmic violence. As the universe evolved, matter collapsed under gravity into the web. When giant clusters formed, the shock waves from those colossal mergers would have rippled through, heating the gas to these incredible temperatures. It's a fossil record of the universe's structure coming together. Solving this is a final accounting. Closing the books on the ordinary content of the cosmos. Finding the WIM confirms our models of the universe's birth and growth are consistent, that no ordinary matter has vanished from the ledger. It completes the picture of the cosmic ecosystem. But if the universe has been hiding half its normal matter in a form we can barely detect, it makes the appearance of something that should be incredibly rare seem all the more startling. The Big Bang was perfectly balanced. That's what the theories say. In that first moment, for every particle of matter, there should have been an equal particle of antimatter. They're perfect mirrors, same mass, opposite charge, and when they meet, they annihilate, a flash of pure energy. If the universe started with that perfect symmetry, all of it should have vanished, leaving just light, an empty, eternal glow. But that's not what happened. We're here, planets, stars, galaxies, a universe made almost entirely of matter. That's the antimatter asymmetry. It's one of the deepest mysteries in physics. Our existence is a cosmic accident, a statistical impossibility that needs an explanation. To find that explanation, you have to look for a crack in the mirror. For matter to win, some rule had to be broken, a tiny bias in the laws of physics that favored matter over antimatter. Physicists call this needed violation charge parity symmetry, CP symmetry. It means the laws should treat particles and their opposites exactly the same, even in a mirror. And we have found small amounts of CP violation in the lab. In certain rare decays of particles called kaons and B mesons, matter and antimatter behave very slightly differently. But here's the catch: the amount we've measured is far too small, by many orders of magnitude. It's not enough to account for all the matter we see in the cosmos. It's like finding a single coin that favors heads when you need to explain a mountain made of gold. So the imbalance must have been forged earlier, in the extreme conditions of the very early universe. Theories like baryogenesis and leptogenesis propose new chapters in that first second. They introduce hypothetical, heavy particles that decayed out of equilibrium, or new forces that interacted differently with matter and antimatter. In these scenarios, for every billion annihilations in the primordial fire, one matter particle was left over. That 1 in a billion survivor is the foundation of everything. Every atom in your body is a descendant of that fragile, preferential process. The hunt for evidence goes two ways. In colossal underground labs and at particle colliders like the Large Hadron Collider, scientists search for any new particle or any greater degree of CP violation that could point to the mechanism. They study the properties of neutrinos with exquisite precision. Some theories tie the matter asymmetry directly to these ghostly particles, and in space, instruments scan the heavens for any sign of primordial antimatter that might have escaped. Could there be entire stars or galaxies made of antimatter? Current observations suggest not. The gamma-ray signature of matter-antimatter boundaries would be unmistakable. And we don't see it. The universe appears decisively one-sided. This isn't an abstract puzzle. It's the question of why anything exists at all. Solving the antimatter asymmetry would write the first page of our cosmic biography. It would explain the initial condition that made life possible. It forces us to look for flaws in perfection, for the subtle broken symmetry that allowed a universe of structure to emerge from pure energy. And if the fundamental laws contain a hidden preference, a thumb on the scale of existence, then finding a particle that shouldn't exist feels like a direct challenge. To our entire framework of reality, a balloon floats over Antarctica near the edge of space. It has an antenna listening for radio whispers from the ice below. That's the ANITA experiment. It's built to catch signals from cosmic rays hitting the atmosphere or the ice. Most of the time, it hears what it expects. But a few times, it heard something impossible, a signal that seemed to come from below, from deep inside the planet. The data suggested these were neutrinos. Ghostly particles that pass through almost anything, but these weren't ordinary neutrinos. Their energy was so high that our standard model says they shouldn't make it through the Earth. At that energy, a neutrino going through thousands of miles of rock should almost certainly interact. It should be stopped. For one to come up through the planet from the other side and reach ANITA, that's like throwing a baseball through a mountain and having it come out untouched. The odds are astronomically small, but ANITA recorded a handful of events that looked exactly like that. So the question was, what could punch through where nothing should? One idea involves a hypothetical particle, a sterile neutrino. The three known neutrinos interact via the weak force. A sterile neutrino would only feel gravity. It would be indifferent to matter. If a high-energy regular neutrino oscillated into a sterile neutrino while traveling through the Earth, it could pass through unimpeded. Then, just before detection, it could oscillate back. That would be a monumental discovery, physics beyond the standard model. Other explanations look at the planet's hidden composition. Could dark matter be concentrated in the Earth's core? If certain dark matter particles decayed there, they might produce a burst of these high-energy neutrinos. That would create an upward-going signal from a point source inside the world. Or maybe the neutrinos themselves have secret interactions, unknown forces that change how they travel through dense matter, letting a fraction sneak through. But the mystery has controversy. Larger observatories like Ice Cube buried in the Antarctic ice haven't seen a corroborating signal. They haven't found a population of these upward-going, ultra-high-energy events. That leaves the ANITA detections in a difficult place. They could be a statistical fluke, a rare background event that mimics the signal, or they could be the first crack in a foundational wall. A hint of new physics so subtle that only ANITA-unique, balloon-born geometry was poised to catch it. For now, these events are a tantalizing enigma. A reminder that profound questions can come from listening to whispers from the ground beneath our feet. That answers to cosmic mysteries might be hidden in unexpected places. Even deep within our own planet, in 2021, astronomers looking at light from quasars saw something, a pattern. It's called the giant arc. It's not a single object. It's an arrangement, a curve made of galaxies, clusters, and gas, and it's enormous, 3.3 billion light-years across. To put that in perspective, if you could see it in the sky, it would cover about 1/15 of the entire observable universe. It's a structure in the distribution of matter. And it's just too big. That size challenges a core idea in cosmology, the cosmological principle, the idea that on the largest scales, the universe should look the same everywhere. No special spots, no giant landmarks. Matter should be like a uniform froth. We know about filaments and walls already, like the Sloan Great Wall, but the giant arc seems to go beyond a theoretical limit. A limit from our models of inflation and how structure forms. Those models say there's a maximum size for any single feature in the cosmic web, and the arc, it gets close to that limit. Maybe even exceeds it. So what does that mean? One option is it's a fluke. The universe is so vast that even in randomness, you might sometimes see a pattern by chance. The question is whether it's physically real. Are those galaxies actually connected by gravity, or are they just lined up by accident from our viewpoint? We need follow-up studies, precise distance measurements, that will tell us if it's a true structure or just a mirage. If it is real, the implications are deep. It could mean the seeds from the universe's first moments, those quantum fluctuations stretched by inflation, weren't as random as we assume. Maybe they had preferred scales we don't understand yet. Or it could point to something exotic in the early universe, influences from before inflation, maybe, or more speculative ideas like cosmic strings, defects in spacetime from the early cosmos, that could sculpt matter into such huge, linear shapes. Now the search is on for other structures at that scale. Projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument are building detailed 3D maps of the universe. They'll tell us if the giant arc is a one-off or if there are many patterns like it. Even as just a candidate, it's a reminder, our maps of the cosmos are still unfinished. The largest structures we can imagine might still be out there, hiding in plain sight, waiting for the right view to show their impossible scale, and from that an immense, slow structure, we turn to the opposite extreme. A signal of incomprehensible energy lasting barely an instant. A cosmic engine can fire more than once. That discovery changed everything. Fast radio bursts were first found in old data. Just a spike of radio waves lasting milliseconds from deep space. For years, every new one was a single event, a brilliant flash that suggested a catastrophic source. Something like two neutron stars merging or a black hole destroying a star, events where the source is destroyed, but then astronomers found one that repeated. And then it did it again, a repeater that meant the object survived. Whatever was making these bursts wasn't being destroyed. It was a machine you could restart. The main suspect is a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's. A magnet so powerful it could erase a credit card from halfway to the moon. These objects are cosmic powerhouses. They have violent starquakes, colossal magnetic reconnection events. A sudden snap in that magnetic field, or a crack in the star's crust, could unleash a titanic blast. That energy travels as radio waves beamed out in a narrow jet. If that beam sweeps across Earth, we see a flash. But the mystery is in the details. The repeating bursts aren't all the same. Some are simple spikes, others show intricate structure, polarization. That polarization is a clue. It tells us the waves have been twisted by incredibly strong magnetic fields on their way out. The environment around the source isn't just extreme, it's dynamic, chaotic. Some theories say the magnetar might have a companion, a cloud of debris, or even another star. As material falls onto the magnetar's surface, it could trigger periodic eruptions like a cosmic geyser. What makes them so valuable is their journey. These bursts travel for billions of years across the void between galaxies. As they do, they pass through diffuse gas. That gas leaves a fingerprint on the signal, a slight dispersion. By measuring that, astronomers can weigh the unseen matter in the cosmic web. They're becoming tools, lighthouses that illuminate the darkness between galaxies. Yet the core question remains: what is the precise trigger? What flicks the switch on a magnetar to produce a burst that, in a millisecond, outshines a billion suns in radio light? Each new repeater adds data, but also complexity. Some repeat on a schedule, others seem random. It's like listening to a cosmic telegraph, but we haven't cracked the code. These fleeting signals are more than anomalies. They're messengers from the most magnetically violent places in the universe, carrying secrets of physics we can't recreate. And if the cosmos can broadcast such brilliant, repeating flashes, it makes a faint, pervasive glow that has lingered since the beginning seem all the more puzzling. The universe's energy budget shows a discrepancy in the infrared. When we add up all the light from every known galaxy, from every star we've catalogued, it doesn't match the total infrared glow we see across the sky. That's the cosmic infrared background excess. It's a diffuse, all-sky light, a kind of leftover warmth from all the stars that have ever shone, and our accounting is off. There's more of this ancient heat than our ledgers of galaxies can explain, so the question is where the extra heat comes from. The leading idea points to galaxies we haven't seen yet. Not the bright, obvious ones, but vast populations of faint, dusty galaxies from the early universe. In their youth, galaxies were often choked with dust from furious star formation. That dust absorbs the visible and ultraviolet light from hot young stars. It heats up, and then it re-radiates that energy as infrared. These galaxies are effectively cloaked. They're missing from our optical surveys, but their collective warmth still fills the background. It's like sensing the heat from a hidden city by the glow it gives off, even if you can't see its lights. This is where new eyes make all the difference. The James Webb Space Telescope was built for this. Its powerful infrared instruments are designed to peer through that cosmic dust, to see the first galaxies in their dusty nurseries. Every deep field image it takes is a search for these hidden contributors. By finding them, we can complete the census of star formation across time. We can finally balance the universe's energy books, yet there are more speculative possibilities. Could some of this excess come from processes entirely separate from stars? One exotic idea involves primordial black holes. These would be tiny black holes, some no larger than an atom, forged in the intense pressures of the Big Bang itself. According to Stephen Hawking's theory, such black holes would slowly evaporate, emitting radiation as they fade away. A vast population of them evaporating across cosmic history could contribute a faint, steady infrared glow. Another frontier theory looks to dark matter. If certain hypothetical dark matter particles decay or annihilate each other, they too could release energy, potentially in the infrared part of the spectrum. For now, the hunt is focused on the dusty galaxies. Solving this excess is more than an accounting exercise. It's about writing a complete history of cosmic dawn and high noon. It tells us when and how stars truly lit up the universe, and how much of that light was immediately swallowed and transformed by dust. The infrared background is the universe's thermal memory. And that memory suggests whole chapters of stellar history are still hidden, waiting to be read in the warmth between the stars. If the total energy of the cosmos holds such a gap in our understanding, it challenges something even more foundational. It challenges the very constants that underpin our equations. The laws of physics depend on numbers we assume are fixed. There's the fine structure constant, alpha. It's a pure number, a combination of other constants. It sets the strength of the electromagnetic force. It controls how electrons bind to atoms, how light and matter interact. For decades, physics has assumed alpha is the same everywhere and always has been. It's a cornerstone, but if that cornerstone isn't solid, astronomers can test this. They use the universe as a time machine. They look at light from incredibly distant quasars. That light travels for billions of years. It passes through clouds of gas between galaxies. Atoms in those clouds absorb specific wavelengths from the quasar's light. It creates a barcode, dark lines in the spectrum, where those lines depends on the value of alpha at the time and place the absorption happened. When scientists analyze these ancient barcodes, some teams report a faint signal, persistent. The lines appear shifted, a tiny amount, almost imperceptible. The implication is staggering. It suggests billions of years ago, in certain directions, alpha was minutely smaller, a change of just a few parts in a million. But in fundamental physics, that's a canyon. If it's true, our constants aren't constant. The fabric of reality might have been woven with slightly different threads long ago. That would be a revolution. It would point toward theories like string theory, which naturally allow for such variations across space and time. The cosmos would have a preferred direction, a fundamental anisotropy, challenging our most cherished principles, but this claim is fiercely contested. Other quasar studies with equally precise methods find no variation at all. The measurements are at the very edge of our capability, where systematic errors, tiny miscalibrations in the instruments, subtle effects in the interstellar medium can mimic a signal or hide one. The debate drives a quest for greater precision. On Earth, physicists use atomic clocks, the most accurate timekeeping devices ever built. They hunt for any present-day drift in alpha. By comparing different types of clocks over years, they can probe for changes so slow they'd be invisible in a human lifetime. So far, these lab experiments show no change. The constant appears constant now, so there's a tension between the deep time astronomical hints and the rock-solid laboratory results. That's the heart of the mystery. Is the quasar signal a subtle error we haven't uncovered yet? Or is it a real whisper from an early universe where the rules were subtly, fundamentally different? Resolving this isn't just about one number. It's about whether the laws of physics are truly eternal and universal, or if they have a history, an evolution written into the oldest light we can see. It challenges the static stage we thought the cosmic drama unfolded on, and if the universe's most basic settings might have been adjustable, then it makes the existence of an object spinning at the absolute limit of physical law seem like a defiant statement. Some neutron stars spin, but some of them they devour. There's a type called a black widow pulsar. It's a predator. There's one, PSRJ 1311-3430. It spins more than 390 times a second. That's a beacon, a fierce wind of radiation and particles, and it has a companion star. They're locked together. Their orbit is tight, frantic. They complete it in just 93 minutes. That closeness is a death sentence. The pulsars blast its energy and wind. It's stripping the companion star, layer by layer, evaporating it into a stream of gas. Over millions of years, this has whittled the companion down from a star to something else, something bizarre. An object barely heavier than Jupiter. This is stellar cannibalism, a system balanced on a knife's edge between destruction and a strange, stable orbit. The physics here pushes every model. The companion isn't just pulled apart by gravity, it's being cooked, blown away by the pulsar's radiation pressure. That creates an environment, superheated plasma, magnetic fields. It's a laboratory for high-energy physics we can't replicate. The very existence of these systems challenges our understanding. How binary stars evolve? How did they get so close? What keeps the companion from being vaporized completely? Some models suggest the ablation is so efficient it creates a cocoon of gas. And that gas shields it from the worst of the pulsar's fury. It's a feedback loop, destruction and preservation. These are extreme endpoints of stellar evolution. More than curiosities, by studying the pulsar's ticks, its precise timing, astronomers can measure things: the orbital decay of the system, the effects of general relativity. They can weigh the tiny companion with incredible precision. These are natural experiments. They test the mechanics of pulsar winds, the process of mass transfer. The ultimate fate of stars in a violent dance. The Black Widow shows us a kind of relationship, one of ferocity and precision, where one object's life is defined by its slow consumption by another. This violent, intimate tango between two stellar corpses, and it stands in contrast to something else, a signal that seems to come from nothing, a whisper from the empty fabric of space itself. The most accurate calculation in physics gives an answer that's spectacularly wrong. Quantum field theory says empty space isn't empty, it's this seething foam. Virtual particles, pairs of particles and their antimatter twins, they flicker into existence. They borrow energy from the vacuum just for an instant and then annihilate. That quantum jitter should add energy to every bit of space, and when you add up all those possible fluctuations from every particle and field we know, you get a number for the vacuum energy density. The result is monstrous. It's not just large, it exceeds the value we actually observe for dark energy, the thing driving cosmic expansion, by a factor of 1 with 120 zeros after it. That discrepancy is so vast it defies any analogy. It's the single worst mismatch between theory and observation in all of science, the vacuum catastrophe. The cosmological constant problem, the math isn't flawed, the calculation is sound based on theories that work incredibly well. The catastrophe is that the universe seems almost perfectly balanced against that titanic background energy. The dark energy we measure is incredibly tiny, but not zero. It's as if the vacuum energy dial was set with unimaginable precision to a value just above nothing, allowing for the gentle acceleration we see. So why doesn't that furious quantum foam generate the crushing repulsive gravity the math predicts? Gravity that would have torn the cosmos apart before any structure could form. The answer has to be a gap in our understanding, something missing that reconciles the quantum world with gravity. One idea is a hidden symmetry like supersymmetry, where every known particle has a super partner. In a perfectly supersymmetric universe, the positive and negative contributions would cancel out exactly, leaving zero. But we don't live in that perfect universe. Supersymmetry, if it exists, is broken. The cancellation would be almost complete, maybe leaving behind the tiny residue we call dark energy. Another approach is more philosophical, the anthropic principle in a multiverse. Countless universes bubble into existence, each with a randomly selected value for the vacuum energy. In most, the energy is too high or too low. The universe either blows apart instantly or collapses too fast for stars and planets. We find ourselves inevitably in one of the rare, finely tuned universes where the value allows us to exist. It's a cosmic selection effect. For many, though, these feel like workarounds. The vacuum catastrophe is a screaming signpost. Our two foundational theories, quantum mechanics and general relativity, they're incompatible at their core when it comes to describing the energy of nothingness. Solving it might require not just a new particle or symmetry, but a revolution in our conception of spacetime itself. This anomaly isn't about a distant star or a strange particle. It's about the fabric of reality we occupy every second, a number so wrong it hints that our most basic picture of the cosmos is still a rough sketch. And if our understanding of cosmic energy is this profoundly off, it makes the unexplained absence of certain colossal structures in the modern universe all the more intriguing. Galaxies are built on collisions. That's the story. Smaller islands of stars coming together over billions of years, merging into the shapes we see. and each galaxy, we think, has a supermassive black hole at its center. So when galaxies merge, their black holes should find each other, drawn together by gravity, starting a final dance, a binary pair whirling closer until they coalesce. A burst of gravitational waves shaking spacetime. It's an elegant story. It's how we think galaxies grow. But when we look at the centers of merged galaxies, we find silence. The tight binaries, the ones in the final death spiral, are almost nowhere to be found. It's not that we see nothing. We find black holes in pairs separated by thousands of light years. We see quasars, brilliant beacons that suggest dual engines at vast distances, but the final act, the last parsec problem, remains a problem. A parsec is about 3.26 light years. Theory says that as two black holes close to within a parsec, they run out of things to slingshot away. They've cleared their neighborhood of stars and gas. With nothing left to steal momentum from, their inward spiral stalls. They become stranded, locked in a stable orbit that could last longer than the current age of the universe. If that's true, the cosmos should be filled with the faint hum of these stalled binaries, but our searches for their signals in light and radio waves have come up empty. That leaves two possibilities. Maybe the final parsec isn't a barrier. In a gas-rich merger, vast disks of material could keep funneling toward the center, providing the friction to drive the black holes together quickly. Their merger would be swift, leaving only a brief window to catch, or their interaction with the galactic core is more efficient than we thought, involving not just stars but whole clusters of stars. Ensuring the dance never truly stalls, the answer is written in ripples we can't yet see. The upcoming LISA mission is designed to listen. This space-based gravitational wave observatory will be sensitive to the low-frequency hum of these binaries in their final centuries and minutes before collision. LISA won't just find them, it will chart their orbits, weigh them, trace the history of galactic mergers through the waves they emit. Its data could solve the final parsec problem. By showing us these mergers are either incredibly common or surprisingly rare. Until then, this absence is a quiet anomaly with loud implications. It asks us to refine our picture of galactic nuclei, to see them as dynamic, messy places where the simple rules of two-body physics are woven into a richer, more violent tapestry. The missing binaries remind us the universe often hides its most dramatic events. Not in brilliant flashes, but in the subtle gaps between our expectations and the silent, dark hearts of ancient galaxies. And if the universe's largest mergers leave such a faint trace, it draws a parallel. To the subtle, rhythmic imprints cosmic cycles might leave closer to home on our own living world. The rhythm of life on Earth is written in stone, and it has this strange, slow beat. For over 500 million years, the fossil record shows a pulse, a cycle in diversity, and in the great periods of loss, repeating roughly every 62 million years. Now, this isn't a space anomaly in the traditional sense, but its source might be far beyond our planet. The pattern comes from deep time, from the rise and fall of ancient seas and the creatures in them. It suggests the great sweep of evolution might not be driven just by forces here on Earth, that the cosmos itself could be setting a metronome for life. So the leading cosmic hypothesis looks at our solar system's journey. Our sun doesn't just orbit the center of the galaxy, it also bobs up and down, oscillating through the plane of the Milky Way like a horse on a carousel. A full cycle of that vertical motion takes about 60 to 70 million years, and as we pass through the denser mid-plane of the galaxy, the gravitational environment changes. The Oort cloud, that vast shell of icy bodies at the edge of our system, could be disturbed. That might send showers of comets inward, increasing the chance of impacts. Or the density of interstellar gas and cosmic rays could fluctuate, possibly affecting Earth's climate and life in subtle, long-term ways. The timing is close to the biodiversity cycle. It suggests a possible link, a cosmic driver for biological change. But the case isn't closed. Many scientists point to Earth's own internal rhythms. The movement of tectonic plates drives cycles of volcanism and mountain building, which can dramatically alter climate and sea levels over tens of millions of years. And life itself has its own dynamics. Ecosystems may reach peaks of complexity and then become fragile, susceptible to cascading collapse. These purely terrestrial explanations are powerful. They have to be weighed carefully. The 62-million-year signal is compelling, but it's also subtle. Buried in noisy data spanning 500 million years, is it a real external clock or a statistical phantom from the complex interplay of geology and biology? Regardless of the cause, the idea is transformative. It blurs the lines between astrophysics and paleobiology. It suggests the story of life on our planet isn't an isolated play. It might be a story written in part by the architecture of the galaxy we call home. If true, it means the rise of the dinosaurs, their disappearance, the ascent of mammals. These could have chapters dictated by our position in the Milky Way. The cosmos wouldn't be a passive backdrop. It would be an active participant in the narrative of life. This cycle represents the ultimate connection. A whisper from the galactic scale, imprinted onto the fossilized record of existence. From the quantum vacuum to the fossil record, these cosmic anomalies form a constellation of questions. Each one is a point of light where our understanding dims, where the map of reality frays at the edges. They aren't failures of science, they're its essential fuel. They are the unknown territories that call us to explore. They remind us the universe is far stranger, more dynamic, more wonderfully puzzling than we ever dared to assume. Our journey is just beginning. With every new telescope, every deeper simulation, every bold idea, we step closer, turning these anomalies into understanding. And in doing so, we redraw the boundaries of the possible. These cosmic riddles, they form a pattern. When you step back, you see it. They aren't just errors on a map. They're the edges of the map itself. Each one, the missing lithium, the silent black hole binaries, they all point to the same frontiers, the nature of dark matter and dark energy. The extreme conditions of the early universe, matter under pressures we can't replicate, maybe new forces, new particles. These puzzles aren't failures. They're our most valuable guideposts. They show us exactly where our elegant models are incomplete. They tell us where to look next. This questioning, it's the engine of science. It doesn't work by polishing what we already know. It advances by confronting the stubborn detail that won't fit. The anomaly that whispers your story isn't finished. This pursuit drives innovation. To hear the cosmic dawn, we build antennas in remote deserts. To weigh a neutron star from light years away, we put instruments on the space station. To catch the ripple of colliding black holes, we suspend mirrors in vacuum chambers 4 kilometers long. Each mystery demands a new way of seeing. It pushes technology to its limits and then beyond, inventing tools that open new windows on the cosmos. Theoretical frameworks stretch in response. The vacuum catastrophe, that profound mismatch, it isn't just a number. It's a mandate for a theory of quantum gravity. The odd behavior of galaxies forces us to test modified gravity against dark matter. The Lithium Problem, the Matter-Antimatter Asymmetry, they send us digging deeper into the physics of the first 3 minutes. These aren't academic exercises. They're attempts to rewrite the foundational rules of reality, guided by the clues the universe left for us. Today, we're not just passive observers of light. We're entering the era of multi-messenger astronomy. We combine the oldest photons with the newest neutrinos. We correlate gravitational waves with flashes of gamma rays. We're learning to read the cosmos in every language it speaks. This integrated approach is how we'll solve these puzzles. A single strange signal from one telescope might be a curiosity. But when that same event rings the universe like a bell, sending out ripples in space-time and a shower of particles, it becomes a Rosetta Stone. The collective weight of these anomalies, and the many more we'll discover, it tells a consistent story. Our universe is richer and stranger than our 20th century physics ever dreamed. The mysteries aren't signs that we're lost. They are the stars by which we navigate into the unknown. They prepare us for a deeper reflection. What does it mean to live in a cosmos that is so fundamentally and so wonderfully unresolved? Looking at these 25 cosmic anomalies, you start to see a picture. We live in a universe that's not fully understood. There's the tiny tug on a spacecraft just millimeters per second, and there's the void, a billion light years across. Each one is like a beacon. They're not flaws in our science. They're the edges of it, the places where our maps run out, where the known laws of physics meet something else, something deeper. You can see a pattern, the missing lithium, the matter-antimatter asymmetry. They're bookends on the first moments of everything. The flat rotation of galaxies, the outlines in colliding clusters, they sketch out dark matter. The vacuum catastrophe, the accelerating expansion, they point to cosmic energy, something we haven't resolved. These aren't just separate curiosities. They're connected, they're clues in one big investigation. They tell us dark matter and dark energy aren't just placeholders. They're the main characters in the story, and we don't know their names yet. That's why these puzzles matter. They're the cutting edge, the questions that keep scientists awake, that drive billion-dollar missions, that make people look up and wonder. The hunt for sterile neutrinos under the ice, the design of LISA, a gravitational wave observatory in space, the James Webb Telescope and its infrared gaze. Each one is a response to an anomaly we can't explain. We build new tools to ask new questions, and the cosmos shows us deeper layers of mystery. This process, observation, questioning, exploration, it's how we rewrite the textbooks. How we move from confusion to understanding. Every big discovery started with a detail that didn't fit, a wobble in the orbit of Uranus, and then we found Neptune. A shift in starlight that confirmed Einstein, the faint cosmic microwave background that proved the Big Bang. Our anomalies today are like those wobbles. Those shifts, they're the prelude to the next revolution. So the universe isn't a museum of settled facts. It's a puzzle, and it's evolving. We're the ones trying to solve it. The greatest discoveries are still out there, in the subtle signatures of data, in the gaps between theories, in the next anomaly that challenges everything we think we know.